Hello, Mr. Betts here. I want to take a look at a few examples that use the first derivative test to determine relative extrema. So remember with the first derivative test, we're looking for where the derivative changes signs. Let me write that a little clearer. So we're looking for where the derivative changes signs. And also remember that the derivative can only change signs at critical points. So the first thing we're going to do is look for critical points. For that, we're going to take the derivative. So derivative here, x over 2 is the same thing as 1/2 times x. So the derivative there is going to be 1/2 minus the derivative of sine is cosine. And we want to know when that is equal to 0. So finding critical values, we want to know where the derivative is undefined or where the derivative is equal to 0. This derivative is always defined, but it is going to be equal to 0 when cosine of x is equal to 1/2. So I'm going to draw a triangle here. So 1/2 cosine is going to be adjacent over hypotenuse. So this will be our angle here, which is going to be pi over 3. So we get a critical value at x equals pi over 3. Remember, so cosine is positive. Cosine is also positive in the fourth quadrant, so we should get an answer somewhere between 3 pi over 2 and 2 pi. So we have one answer here at pi over 3, another answer here at negative pi over 3, which is going to be 5 pi over 3. So we are going to get critical values where cosine of x is equal to positive 1/2. Remember, cosine is positive in the first and fourth quadrants. So we need to get both of those angles because we are looking at all angles between 0 and 2 pi. So now that we have the critical values for the first derivative test, we want to know where the derivative changes signs. The easiest way to explore that is by using a sign chart. So I'm going to make a sign chart for the first derivative. We are restricted to the interval from 0 to 2 pi. I want to make sure I don't just put my two critical values on here and leave it open on the ends, because that implies that we're going to go to negative infinity and positive infinity, and we are not. So I'm going to stop this at 0 and 2 pi just to show that we are only on those intervals. So now I need to know, is the derivative positive or negative on each of these intervals? I know that this is an open interval to the left and it does not include 0, but the sign at 0 for our derivative is going to be the same as the sign at, say, pi over 6. So I'm going to use 0 to plug in for this interval. Again, I know it's not on that interval, but it's the endpoint, and the sign, the positive or negative, will be the same. So plugging 0 in to our derivative, cosine of 0 is 1. So we're going to have 1/2 minus 1. That's going to give us a negative value. If we plug in a number like pi over 2 on this interval right here, cosine of pi over 2 is 0. 1/2 minus 0 is 1/2. So this is going to give us positive. And then in the last interval, again, I know 2 pi is not on that interval, but the sign that we get on the derivative will be the same. So I'm going to plug in 2 pi. And if we plug in 2 pi, cosine of 2 pi is positive 1. 1/2 minus 1 is negative 1/2. So we're going to get negative values there. So we know, based on this sign chart, that the function itself is decreasing on the interval from 0 to pi over 3. The function is increasing from pi over 3 to 5 pi over 3. And then the function is decreasing from 5 pi over 3 to 2 pi. What we want to know is where the derivative changes signs, what kind of relative extreme are we going to get? So I'm going to start with pi over 3 here, and I'm going to write out my answer. F has a relative. So the derivative does change signs there, so we do have an extreme. Since the function is changing from decreasing to increasing at that point, we're going to get a relative minimum. So F has a relative minimum at, and then it does say find the relative extrema, so we want to find these as points. So this is going to be pi over 3, comma, it's going to be f of pi over 3. So just a little side work here. F of pi over 3 is going to give us pi over 6, because I'm dividing by 2, minus the sine of pi over 3. Sine of pi over 3 is going to be square root of 3 over 2. So we get pi over 6 minus square root of 3 over 2. And then we should justify our answer. I know the problem doesn't say to do that, but I'm going to go ahead and do that. So because f prime changes from negative to positive at that point. Okay, so remember, when the derivative is negative, the function's decreasing. When the derivative is positive, the function's increasing. So at the point where the derivative changes from negative to positive, the function changes from decreasing to increasing, and we get a relative minimum. So then the other point that we're going to have here where the derivative changes signs is going to be at 5 pi over 3. This time, this is going to be a relative maximum. Because the derivative is changing signs from positive to negative. So where the derivative changes from positive to negative, the function changes from increasing to decreasing, and we get a relative maximum. So this is going to be at 5 pi over 3, comma. So this is going to be pi over 6. The sine of, I'm just going to modify this up here. The sine of 5 pi over 3 in the fourth quadrant, sine is negative. So the only difference here is that we're going to add square root of 3 over 2 instead of subtracting it. And we want to justify because f prime changes from positive to negative. So we have two relative extrema. I do want to point out that because the function is decreasing over the first interval, that endpoint could be considered a relative maximum, except that it's an open interval. And so as we approach that left endpoint from the right, we're not going to get to some maximum value. It's going to be increasing as we approach, and it's going to get bigger and bigger and bigger, but there's no biggest value. And by the way, when I say bigger and bigger and bigger, it's not getting really big, it's just approaching from below. So if we look at what the graph of this looks like, remember we had a derivative that was negative on that first interval, a derivative that was positive on the second interval, and then negative again. So the graph matches what we got for our derivative, and we got a relative minimum where that derivative changed from negative to positive. So the function changes from decreasing to increasing. All right, remember, we don't want to mix negative and decreasing or positive and increasing. So when we say f prime is negative, that's the same thing as saying f is decreasing. It is not the same thing as saying f prime is decreasing. So again, be careful about the language that you use, but we can see here that where the function changes from decreasing to increasing, we get this relative minimum. And likewise, where the function changes from increasing to decreasing, we get that relative maximum. Okay, second example, I'm going to go through this one with a little less explanation. We're looking for relative extrema, so we're going to start by finding critical values. Notice that we didn't restrict the domain here, so we're looking at all real numbers, and we're going to start by taking the derivative. So the derivative here would be 2/3, and then x squared minus 4 to the negative 1/3. That's using the power rule, and then we have to multiply by the derivative of the inside function, which is 2x. So cleaning that up, we're going to have in the numerator, we're going to have the 2 times 2x, which is 4x. In the denominator, we're going to have 3x squared minus 4 to the 1/3 power. So critical values we're going to get where the derivative is either equal to 0 or the derivative is undefined. And this is actually the first example we've seen where we're going to get varieties of both. So the derivative is going to equal 0 when for x equals 0. So essentially, I'm just taking the numerator and setting it equal to 0, because if the numerator is equal to 0, then the whole thing is equal to 0. So we get a critical value at x equals 0, but we're also going to have the derivative undefined when the denominator equals 0. So we can solve this by doing some manipulation here. Divide by 3 on both sides, raise both sides to the third power, and essentially what we get is x squared minus 4 equals 0, or x plus 2x minus 2 equals 0. So we also get critical values at, I'm going to write this underneath here, critical values at x equals 0, because that's where the derivative equals 0, and also at x equals -2 and x equals +2. And remember, critical values only occur when the function itself is defined. And if I plug any of these values in particular the ones in question might be where the derivative's undefined, I can plug those into g of x and get values. So these are critical values for the function. If the function itself was not defined at those points, then I would throw these out. But it is defined, so we are not going to throw them out. Okay, so the next thing I'm going to do is I'm going to make a sign chart. So I want to know where the derivative is going to change signs. So my sign chart for g prime is going to include -2, 0, +2. This time I'm leaving the ends open because it does go to -infinity and +infinity. So if I take a really big negative number, so I'm looking at this interval right here, a really big negative number, and plug it into the derivative here, I'm going to get a negative on top, and then on the bottom, this is going to be a really big number, and a really big number to the 1/3 power is going to be a really big number. The important thing is that we're going to get a positive on the bottom, so we're going to get a negative derivative there. So negative there. If we plug in -1, we get negative in the numerator, and then in the denominator, -1 squared is 1, -4 is -3, and a -2, an odd power, an odd root, is going to stay negative, so it's negative divided by negative, which is positive. Now if we plug in +1, we get a positive on top, but we're going to keep a negative on the bottom, so this is going to be negative. And then plugging in a big number, any big positive number, we're going to get a positive divided by a positive, which is positive. Okay, so we do have the alternating feature of our sign chart, which happens very often, but not always, so you do want to make sure you check every interval. All right, so just analyzing what we've got here, we've got a derivative change from negative to positive here at -2. We've got a derivative change from positive to negative at 0, and then another change from negative to positive at +2. So I'm going to write out my answer. So G has, let's start with the, there's 2 of them here, the places where the derivative changes from negative to positive. So G has relative minima at -2, comma, we plug -2 into the function. G of -2 is 0. Keep in mind right now we're looking for points on G, so we're plugging into the function, not into the derivative. And at 2, comma, 0, because G prime changes from negative to positive at those points. Okay, again, notice that I said G prime changes from negative to positive. That implies that G itself changes from decreasing to increasing, and so we get relative minima. At 0, the other critical value, we're going to have a relative maximum. That's a 0 there. So G has a relative maximum at 0, plugging 0 in, we have -4 to the 2/3. -4 squared is 16, so cube root of 16, because G prime changes from positive to negative. Again, notice that we're saying G prime changes from positive to negative, which implies that G changes from increasing to decreasing, and that gives us a relative maximum. So just thinking about what this graph is going to look like, a relative maximum here came from the critical value where the derivative equals 0. So I would expect to see a horizontal tangent at that point. Our relative minima came where the derivative was undefined. So I would expect to see maybe a vertical tangent or some corners at that point, at those points, I should say. And actually, it turns out that we have both. So looking at the graph of G, we do end up with vertical tangents there, but we also end up with a corner there. So our relative minima, the derivative change signs from negative to positive because the function changed from decreasing to increasing. That happened at both of them. And then at the maximum, we get a max because the derivative changed signs from positive to negative. Okay, this last example I'm going to go through a little bit more quickly. So we start by taking the derivative, because we need to know where the derivative is equal to 0 or undefined for our critical values. So we have derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So our critical values then are going to come where the derivative is equal to 0. That's going to be where the numerator equals 0. And then also where the derivative is undefined, so where the derivative's denominator is equal to 0. So it looks like we're going to have 4x to the 5th minus 2x to the 5th. So we have 2x to the 5th minus 2x equals 0. So that's the numerator simplified. We can factor out a 2x, and we have x to the 4th minus 1 equals 0. Then we can factor that x to the 4th minus 1. It's going to be x squared plus 1, x squared minus 1, which is x plus 1, x minus 1. So we get from this critical values at x equals 0. We don't get any critical values here because x squared plus 1 can never equal 0, -1, and at +1. We also want to know where the derivative is equal to 0, so that's going to be x to the 4th equals 0, and that's going to be at x equals 0. So that gives us a critical value there at x equals 0 again. So next thing I want to do is make sure these are actually critical values on the function, so they're defined on the function. And it turns out when we plug in 0, we get 0 in the denominator for the function, so that is not a critical value. If we plug in -1 or +1, we get values for the function. In fact, h of -1 is going to be 2 over 1, which is 2, and h of +1 is 2 over 1, which is 2. So the values that we get for the function at those points are going to be 2. So the next thing I want to do is make a sign chart here. Now, let's see, it's h prime. So our sign chart is going to be for h prime. Let me switch colors here because I'm going to be squeezing things together. And our critical values are -1 and +1. But I also want to include that critical value that we threw out because that is a potential sign change at that point, even though it's not a critical value. So plugging in a big negative number into the derivative. The derivative here, probably need a simplified version of that to do that. So let's go I'm going to cancel one of the x's. So we're going to have 2x to the fourth minus 2 over x to the third. So I canceled an x here with an x in the numerator. So if we plug in a big negative number into this, no matter what we plug in here, that's going to be positive, but it's a big positive. So we get positive on top divided by a negative on the bottom is going to give us a negative derivative. Between -1 and 0, if we plugged in like -1/2, that's going to give us a negative on top, also a negative on the bottom, so we're going to get a positive. If we plug in a number like +1/2, we get a negative on top and a positive on the bottom, so that's negative. And then any big positive number is positive divided by positive, which is positive. So remember, we are not looking for a relative extreme at 0 because that was not a critical value. So we're only going to get relative extrema at -1 and +1. So we do have sign changes there at those two critical values. So H has a relative at -1, we're going to have a relative minimum because the derivative changes from negative to positive. So relative minimum at, this is -1, 2, because H prime changes from negative to positive. And then H has a relative maximum at 1, 2, because H prime changes from positive to negative. Okay, so if we think about what the graph might look like here, we know the function's going to be decreasing and then increasing to give us a relative minimum. Then to the right, we know it's decreasing and increasing, so it gives us a minimum. Also at 0, since we're dividing by 0 in the function, I would expect to see a vertical asymptote there. So if we look at the graph of that function, we get exactly what we expected here. So we have a vertical asymptote at 0 where the function itself was undefined. And then we have a relative minimum at the 2 points where the derivative changes signs from negative to positive. So again, H prime changes from negative to positive means that H changes from decreasing to increasing, meaning that we have relative minima at those 2 points.